We're now going to look at some models that explain power laws. So by that I mean systems of equations that result in power law behaviour. And let's just think back to when we were studying the simple harmonic oscillator, and we saw how if we had equations like this, x dot is proportional to y and y dot is proportional to minus x, that would result in oscillation, simple harmonic oscillation, because if we differentiate this twice, we get x double dot is proportional to y dot, and y dot is proportional to minus x, so we get x double dot proportional to minus x, and that is the requirement for oscillation. So with this understanding, when we see oscillations in our data, we can say, are there two variables that sort of play the role of x and y in these equations? Because if we can identify them, then we've got an explanation as to why they produce this oscillation. And I gave the example of cycles in population and civil unrest. So we suggested that if population pressure plays the role of x and happiness of the population plays the role of y, then we could come up with an argument as to why they were related in this way, and then we would explain why there were cycles of population and civil unrest. And so what we're going to do here is something similar for power laws. We're going to look at three sets of equations that generate power laws, and then with this understanding in future, when we come across power laws in our data, whether it's power laws in the sizes of walls or in the sizes of cities or in the sizes of people's incomes, we can say to ourselves, are there variables involved that somehow interact with each other in the manner described by these systems of equations that we're going to be looking at? So the first one we're going to look at is to do with the idea of elasticity. So if we recall the Weber-Fechner law, we had the situation where the absolute change in one variable, which I'll write as y here, the absolute change dy is proportional to the relative change or the percentage change in the other variable, dy equals dx over x, or I should say just proportional to dx over x. And that was a Weber-Fechner type situation, and that gives rise to an exponential law that x is proportional to e to the y. Well, what we're going to look at now is a situation where it's not the absolute change in y that depends on the percentage change in x, but the percentage change in y. So this will be dy over y is proportional to dx over x. So this is the kind of situation that's often encountered in economics. Economists are concerned about how the percentage change in one thing, like the price of oil, let's say, affects the percentage change in something else, like the unemployment rate, for example. So you're interested in how percentage changes relate to each other. And it's usually written that the constant of proportionality is called the elasticity, and in this case it would be the elasticity of y with respect to x. So, oops. The percentage change in y is related to the percentage change in x by this constant, the elasticity, eta, written with the Greek letter eta. So the elasticity of y with respect to x. And we may recall that dy over y can also be written as d of log y. And similarly, dx over x is d of log x. So we could write this as d of log y equals eta yx d of log x. And then we can take this down onto the other side. So we've got d of log y by d of log x equals eta yx, but I'll just drop the subscripts for now. And here eta is just a constant. Well, we should recall that if we have something like dy by dx equals m, then that tells us that there's a linear relationship between them. The general formula for that is y equals mx plus c, because if we differentiate this with respect to x, m times x, this just becomes m, and the constant disappears, so we get m. So in this case we've got not dy by dx equals a constant, but d log y by d log x equals a constant. So we will have something like that, and it will be with logs. So we'll have log y equals, and the constant here is eta log x plus c. C being a constant of integration, if you like. So we can now raise both sides to the, or exponentiate both sides, do the inverse of the logarithm. So we get y equals, and then this will be x to the power of eta, and this c will become e to the c, which I can just call a, and then I'll just rearrange these. I'll put a x to the power of eta. So this is a power law with the exponent of the power law being equal to this elasticity. And we can see that we've got here d log y by d log x equals a constant, and then we've got that results in log y equals eta log x. So we can see why when we plot log y against log x on double logarithmic axes, we're going to get a straight line, because that's the formula of a straight line. And we see that that comes from the fact that we've got the percentage changes here. So it's because we've got the d log y by d log x that we're going to get this appearing as a straight line on double logarithmic axes. We've got double logarithms. And so we can now sort of see why when we've got Weber-Fechner type law, dy equals k times dx over x, that is dx over x is d log x. So this could be written as dy by d log x equals a constant. Again, just like this, it will result in a straight line. But we've got dy by d log x. So now we can kind of see why with the exponential, which is what this produces, it's semi-logarithmic axes. We have one that's an ordinary axis and one that is logarithmic. And then we get a straight line. So for this that produces an exponential, we want semi-logarithmic, but for this that produces a power law, it's a double logarithmic axis that makes it a linear relationship. So anyway, the basic point is that if we have something like that the percentage change in one variable is proportional to the percentage change in the other variable, then we've got a power law. Now, our next example is just a little bit more involved. It's that of coupled exponentials. So we're going to have two variables that obey exponential laws, and then when we put them together, it results in a power law. So let's see how that works. So let's start off by imagining that we've got some kind of Weber-Fechner law. So we've got the expression 1 over x dx by dy equals a constant, which I'll call u. When we talked about Weber-Fechner laws, we saw that there are various ways we could write them, and this is just one of them. It's just relating dx over x, the percentage change in x, to the absolute change in y. So we got 1 over x dx by dy equals a constant u. And we know that that will result in the solution that x is proportional to e to the uy. So to try and give a kind of concrete illustration for this, not necessarily a very realistic one, but let's suppose that we're talking about wars, and x is the size of the war, so it's the number of fatalities in the war, and y represents the number of grievances that are at stake in the war. And this u, I've called it u because it's standing for a kind of unification principle, so that if u is 0, then the amount of killing will be constant. It won't depend on the number of grievances at stake in the war. So it will mean that the amount of killing is the same whether the war is trivial, doesn't involve many grievances at all, or whether it's very serious, involves a lot of grievances. So if unification is 0, there is no unification. Casualties of wars do not tend to be concentrated. They're the same, whatever the amount of grievance behind the war. But if unification is high, then the amount of killing will increase dramatically with the number of grievances, so that most killing will take place in wars that have a high level of grievances at stake. So U is kind of measuring the tendency for the killing that takes place in war to be concentrated, unified into certain particularly large wars with large numbers of grievances, or to be spread out among many wars. So it's measuring that tendency to unify and concentrate the killing. Okay, now suppose that the probability of a certain number of grievances being at stake in a war also obeys an exponential principle. So we'll have 1 over p times dp by dy equals, in this case, I'll write minus d, because d is going to be a diversification metric. So in this case, we know the solution will be the probability of y grievances being at stake in the war is proportional to e to the minus dy. And d represents kind of diversification, because if d is large, it means that the probability of wars with large numbers of grievances is very small. This decreases very rapidly. If d is large, this will quickly decay to 0. So that means the probability of large y, large numbers of grievances, will be low. And that will mean that wars with large numbers of grievances will be very rare. Most wars will be, have low numbers of grievances. So in other words, people tend to, instead of concentrating all their grievances into one big war, they'll have lots of war covering lots of little grievances. So grievances tend to be diversified into many wars rather than being concentrated into one big war. So the bigger the diversification, the more that's the case, the more that the grievances will be spread out into lots of little wars. Now, before we go on, we need to think about a sort of basic principle of probability, that supposing we have our variable x that can vary along this line, so it can vary between x and x plus dx, and y depends upon x. So when x is x, we get y, and when x goes to x plus dx, this will be at y plus dy. And the probability that x lies in this particular range of values is going to be the probability at x times dx, the probability density times the interval. And similarly here, the probability of y times dy is the probability that y lies in this interval between y and y plus dy. So it's again the probability density times the interval. But because if x is there, then y is there, these must be equal. Because if x lies in that interval, then y will definitely lie in that interval. So the probability that y lies in that interval is exactly the same as the probability that x lies in that interval. So we get this result that p of x dx equals p of y dy, which we can also write as the p probability that of x is equal to p of y times dy by dx, just taking that dx down to the other side. So let's just get rid of this so we can carry on underneath there. So this is just a generic result of probabilities that we will now be using. So we had that p of x, the probability in this case that a war has that number of killings, x amount of fatalities, is going to be equal to the probability of y, the probability that the war has that number of grievances, multiplied by dy by dx. Well, we know what p of y is, we've got it up here, so we'll put proportionality now. So this is going to be proportional to p of y, which is e to the minus dy. And what about this dy by dx? Well, we have x is proportional to e to the uy, so dx by dy is proportional to e to the uy, because when we differentiate an exponential we get the same thing, but we wanted dy by dx, so we need to invert this. So dy by dx equals, well, when we take the reciprocal of that, it will become e to the minus uy. 1 over e to the uy is e to the minus uy. So dy by dx here is just e to the minus uy. So we can combine those exponents, so that means it's proportional to e to the minus u plus d times y. Now we're going to do a little bit of a trick to get this to change into being an x, because you can see that we've got x is proportional to e to the uy, so we've got an e to the y here, so we can kind of sort of start to get this to depend on x, which is desirable because we want to see how the probability of x depends upon x. So what I will do, the little trick, is we're going to write this as e to the minus u plus d over u times uy. So that says u plus d over u, and there's a u there as well, so the u's cancel, so it's actually just the same thing, but I've kind of introduced a u on the bottom and a u on the top. And now that's e to the minus, whoops, sorry, we can write that as e to the uy times minus u plus d over u. I've just kind of rearranged them. I've just put that uy in front here then times minus u plus d over u. And then e to the uy is x from up here. So we've now got x to the minus u plus d over u. And this is a power law then. The probability of x is proportional to x to a constant. U and d are both constants. So we have a power law in x, because remember, you know, the power laws we've been looking at, P of s is proportional to s to the minus alpha. That's our basic power law equation. So in this case, we've got P of x proportional to x to the minus alpha, where alpha equals u plus d over u, or we could write that as 1 plus d over u. And now remember that we were talking about rank size plots. We would have that then the equivalent rank size plot would be that x is proportional to r to the minus beta, where beta was 1 over alpha minus 1. So in this case, alpha is 1 plus d over u. So beta is going to be 1 over 1 plus d upon u minus 1. Well, the 1's obviously cancel, so this is equal to 1 over d divided by u, and 1 over d over u, we just flip it over, that is equal to u upon d. So what we're finding here is that we've got a, for our rank size plot, the exponent beta is u upon d. And you may recall that we talked about Zipf's argument that the is sort of equal, the balanced, when the forces of unification and diversification were balanced, that was when beta equals 1, or when u equals d, forces of unification and diversification balanced. And when beta was less than 1 here, that was when u was less than the diversification, and when beta was a steeper slope, beta was greater than 1, that occurred when unification was greater than diversification. And we suggested that that would all sort of make sense if we had b equals u over beta equals u over d. And now we've seen then that if we have these constants and call them the unification and the diversification constants in this kind of relationship, then indeed it generates that beta equals unification over diversification. Beta equals u over d. So if we find power laws, then we can explain them with these coupled exponentials. We've not only explained the power law, but we've also understood how unification and diversification work in such a system. And so we've kind of given some mathematical rigor to this idea of Zipf. And our third example is to do with issues of cost perception. So people have suggested that the amount of interaction between two places is a decreasing function of the cost of movement between them. And not just a decreasing function, but a decreasing exponential function of the cost of movement. So if we write I for interaction, then we've got interaction proportional to e to the minus beta times c, where beta is some constant and c represents cost. And so by interaction we mean things like trade between two places, travel between the two places, you know, how many people are going from A to B on their holiday or to visit people, or the amount of mail that's going between two places. It's a decreasing exponential function of cost. It falls off very rapidly. That's been a suggestion that's been used in urban modelling. But now we can introduce our old familiar Weber-Fechner law to suggest that the perceived cost is related to the distance between two places by a Weber-Fechner law. So the absolute change in the cost is related to the percentage change in the distance. And we considered this before, the idea that if you're going on a journey of 10 miles, then to go an extra mile would be quite a burden. But if you're going on a journey already of 100 miles, then adding an extra mile to your journey is not so much of an issue. So your perception of the cost is related to the percentage change in the distance, whether it's a 10% increase to your journey or whether it's only a 1% increase. If you know, it's not the absolute change of a mile, it's the relative change that's important. Well, in that case, if we've got such a relationship, we know that the solution to that is C is proportional to log x, as we considered these in the lesson on calculus. So we can substitute this for cost into here. So we've got the amount of interaction is proportional to e to the minus beta times the log of x, where we've got a constant multiplier there. Well, I've absorbed that into this beta, so beta slightly changed its meaning between there and there, but it's still just a constant. So we can then rearrange this to put e to the minus, we'll put e to the log x times minus beta. So I've just put the log x in front of the minus beta second. And then, of course, e to the log x is just x. So we've got the amount of interaction is proportional to x to the minus beta. So if we write the interaction between places separated by a distance x is proportional to x to the minus beta. So we've got a power law. The interaction over distance x is proportional to x to the power minus beta.